and I welcome you to this session. In this session, we'll discuss about the methods for thermal management of electronics or microelectronics. Uh, so can anyone tell me what is the importance of studying this? Why do we need to study the thermal management of electronics? What is the need for thermal management of electronics? To reduce the hotspot? Hmm? To improve the heat transfer rate? In the case of batteries, to avoid thermal runaway? Right? So this problem has arisen because we all want our phones, our laptops to be sleek, to be slim, right? There's a continuous kind of competition to make your devices very small, right? We have a Moore's law. Moore's law say that in every uh, somewhat in I think in every 2 years or every 5 years, the number of transistors which you can print on the chip, it jumps one order of the log scale, right? So keeping that in mind, we as a thermal engineers have a responsibility to design such systems in such a way that these systems they don't fail. So in microelectronics, what we usually follow this MTBF. It is also defined as the mean time between failures, and it is proportional to e raised to the power 1 by t. So as you operate at higher and higher temperatures, the time between the failures it reduces. It means that your device is more susceptible to failure, or its reliability will decrease, right? So that is because of temperature. These devices, they have very small junctions, the area is quite small, and in most places we have heterogeneous structure. It means that one structure may be made of gold, one can be of some other material, and all these materials they have different thermal conductivity or thermal values. So even they have different thermal expansion coefficients. So when they expand, there can be a kind of a junction failure occurring there. So that is why it is very important for us to manage the thermals of our electronics. The performance also degrade when the device becomes very hot. So this all micro packaging and these things, it started in early 1980s, 1990s, when companies like Intel, Cray, they went on to develop these small transistors, these small chips, and then they were packed into some kind of systems which has these input output pins or junctions, and these packings were of different types. As this is called the small outline packing. In the small outline packing as well, we have the T-SOPs and S-SOPs. So T-SOPs, they stand for thin small outline packing, and S-SOP, they stands for shrink small outline packing. So all these packings, they were very small, and inside these packing what we have is that, let's suppose I try to draw the image of a schematic of this transistors by cutting them from the cross section. So what they have a die. Now this die is any semiconducting device. On the base we have die plate, then we have the junction of the wires coming out from this, which maybe it can be in form of pins, which then get embedded to the PCB board, and then we have an outer casing out of that. And maximum of the heat is produced in this die. So they were designed in such a way that they always had kind of a road to, so that heat can flow, or a circuitry so that heat can flow. So it can be any metal like copper which can allow the heat to flow. So these are called the heat pathways. So this heat, it can either be transmitted to the board which sits below this device, or to the casing which covers this device. So then the next challenge was how to remove the heat from this board and this casing. Until we had not a very high density of fabrication, until that time the natural convection was doing this very efficiently. So this was all placed inside your boards, and then using natural convection the heat transfer was happening, and they were able to manage the junction temperature somewhere around 80 to 90 degrees Celsius, or as required by the machine or the device. And these were very popular in old TVs or VCRs or CD players. But as we have gone into higher density fabrication, the chips, the densities, the heat flux which comes from these devices is very high. So right now the gold standard is if we are able to make a heat sink for device that produces 1 kilowatt per centimeter square of the heat, then that is what is the requirement of the industry. And if I just give you a comparison, the heaters which you use in winters, that heater is usually of 1 kilowatt. So that whole of 1 kilowatt is just coming from 1 centimeter square of area. That much thermals you have to manage. So that is the primary need of having the thermal management of electronics. And we also have different type of packagings like this LPS CPS. This is called lead frame chip scale packaging. Then we have FCPGA and we have FCBGA. Here this P stands for pins because under this chip we have pins, and this B stands for balls. So this just fits onto your PCBs, and that's how these devices they work. To go a little bit further into the terminology of the thermal specification of microelectronics. So when these thermal engineers they design these devices, they design in such a way to cater certain parameters. The first one is junction to air thermal resistance. Now before explaining this, we must know what is junction. So we know that in the die the heat is being produced. Junction is the point where we have the maximum temperature. So the point of maximum temperature in this device is called a junction. And to define junction to air resistance, we can simply write it, resistance junction to air is equal to temperature of junction minus temperature of air divided by heat flow rate, right? So in this case what we have to do, we have to take in consideration the resistances of first the mode of heat transfer from junction to the casing and the board will be conduction, and then from this casing and the board the mode of heat transport will be convection and radiation. So this parameter, which is the RJA, the thermal resistance from junction to air, it is defined as Tj minus Ta. It is what is being required as a thermal engineer, so we have to design a system in such a way. There are other thermal resistances as well. One is junction to case and other one is junction to board thermal resistance. So as I have already mentioned or discussed that we have a die here, then we have a die plate, then we have certain terminals, and then we have a casing. And this device, it sits on a PCB board. So we also have a PCB board. Now when the heat is produced, it flows either to the casing or some part it goes to the casing and some part it goes to the board. So when we define junction to case thermal resistance, we define it as RJC is equal to temperature of junction minus temperature of casing upon heat transfer that has occurred between from junction to case. Similarly, we also define junction to board thermal resistance as RJB is equal to temperature of junction minus temperature of board upon QJB. So as you can see in both these cases, the mode of transport of heat is only conduction. The heat transfer which occurs due to the pathways which are already embedded in this device. But the next question is, how do we measure this? How do we know that how much of heat is being transferred to this casing or to the board? For that, there is an agency called JEDEP. It has specific standards, it has specific guidelines according to which we can say standardize all these terms. So you have to measure what is the heat transfer from junction to casing, what we do is we install, in that case of course there is no board, so we install insulated material on all the sides. So we have insulation material here, we have insulation material here, and we have insulation material here. So in this case, all of the heat transport that will occur to the casing, and then we measure the temperature on the casing, and then we define this RJC value, the junction to casing thermal resistance. This is insulated, right? Similarly, in the case of RJB, where we have to find how much heat transport occurs from your junction to board, in that case what we do is we okay, so I'll draw it here. Again, in this case we install insulation on the bottom side and on the top side. Of course, in this case we have a board. And then on this side we have liquid channels, and here we have water channels. And then a specified amount of or flow rate of liquid is flown from these channels, so that this is a cold plate. This is maintained at a lower temperature. And then the heat transport route would be from the die through this board to this cold plate. And then we measure temperature on this board, and that gives us the temperature value of TB, and using that we can quantify how much is the heat transport that occurs to the board. In this, of course, we assume that all the heat is being transferred to the board, through the board to this cold plates. So this is how we define the junction to case temperature and junction to board temperature. Also, one thing which I should have mentioned in this case, where we have defined the junction to air temperature, is that this is also standardized. So we control the parameters here also. What we usually do is that we take a cube, not a cube exactly, we take a box. On that board we have a holder, and from this, on a cantilever, we put our device, and then this device is operated, and then the air temperature we measure at a certain distance below this device. Let's say this is XA, this is the point A, and the dimension of this cantilever is different for different devices. Let's say if the size of this device, the side of this device is less than 27 millimeter, oh sorry, 2.7 millimeter, its size is its size is defined by 76.2 millimeter cross 114.3 millimeter, the size of this cantilever on which this device is placed. And if its size lies between 4.5 millimeter and 2.7 millimeter, then in that case the size of this cantilever is also defined. It is 101.6 millimeter times 114.3 millimeter, and this thermocouple is 2.25.4 millimeter below this device. So that is just defined by this agency whose name is JEDEC, and it is also known as Joint Electronics Device Engineers So this agency gives the standard, so that whenever when any manufacturer is making devices, they have to comply by these standards to give us the what is the resistance of this device from junction to air, what is the resistance of this device from junction to board and junction to casing. Right. Where? Which case? Here. So see, what will happen is that in this case we expect natural convection. So natural convection will affect the temperature which is above this device. So as to have a fair bit idea of what is the mean temperature in whole box, that's where we keep this thermocouple. Uh, so it's waiting for the entire environment to come at steady state, but it has certain openings as well. And this is just for the you see the natural convection. If you have to design a device in where you are using a forced convection, like you are using a fan, then this dimensions are different. In that case, you take a very long channel and you flow some air from the fan using at certain like volumetric flow rates. But these are all standards which any manufacturer they have to comply with as to give some value so that they can say or compare with other products that their resistance from junction to air is this value, right? Yes. So next one is junction to top thermal this junction to top thermal parameters, and so in most cases it is very difficult to measure the heat which is flown to only to board or only to junction at several points, right? So usually now these industries what they do is they don't define the junction to top or junction to board as thermal resistance. They define it as thermal parameters or thermal characterization parameters. And what they do is that they define this psi is equal to the top terms, it remains almost same. So junction minus top, or you can say casing, but this term it is Q, not the Q from junction to board or junction to casing. So this is the total heat which is being produced by the device. So this parameter is now usually used. Earlier it was junction to top thermal resistances, but now it is shifted to junction to top thermal characterization parameter. Similarly, you can use the same parameter for the board. So we can define it as Tj minus Tb by Q. If you remember, in the case of thermal junction to board thermal resistance, it was Rjb is equal to Tj minus Tb by Qjb. It was from junction to board heat transfer rate. But now we define it as how much heat is being produced in the device that we use here, right? So these are just simple design parameters which you must be careful of. One more important thing is that the thermal resistance networks. So these thermal resistance networks are very important when there are multiple thermal resistance in series. Example, we have a device. I'm taking a very complex diagram. So let's say we have a device here. It's a transistor, but heat is never produced on the top of transistor. It's inside a transistor. So here there can be several contacts here, and each contact will have its own thermal resistance. Then it is lying on a thermal interface material. It will have its own thermal resistance. Then it's being packed by the casing. It will have its own thermal resistance. Then we have various interfaces here. It will have its own thermal resistance. Then on the thermal interface material side, it will have a heat sink. It will have its own thermal resistance. So this becomes a very complex problem to address to. So simplify it, we mostly rely on these thermal network diagrams. So let us suppose that we take the initial example where we are having a die, and on this die we have some junction temperature Tj, and then of course it is connected to the casing and the base or the board on which this device is lying. So in that case, simply we can just solve it by making an equivalent thermal resistance diagram as, let's say this is your junction temperature Tj and this is your ambient T infinity. So half of the heat it will, or some portion of the heat will flow through the junction to your casing. So we can write it at RJC, and then there will be a thermal resistance also further between your casing and the air. So RCA. Similarly, some portion of the heat will be transported through conduction via to the board, so we can call it RJB. And then further, there will be a thermal resistance between your board and ambient, so we call it RBA. So these are the thermal resistance networks. Just a revision of what you have studied in your heat transfer. This we are revising because we'll also be solving certain problems in this class, and there you will need this kind of revision. So if you have to write the equivalent circuit for this, so let's say this is Tj and then Rja, and then we have T infinity. So the equivalent thermal resistance would be, I think you can all, what would it be? It would be equal to 1 over RJC, because these two are in series, and then these two are in parallel connection. So we have RJC plus RCA plus 1 over RJB plus RBA. Understood? Further, we can write it as RJA is equal to RJB plus RBA times RJC plus RCA whole divided by the sum of all these four resistances. So it would be RJB plus RBA plus RJC plus RCA, right? Remember that this RJC and RJB, their resistance is due to conduction, and this RCA and RBA, these are this resistance because of convection and radiation, right? Now let me ask you this. So what do you think the R between junction and ambient would be if your thermal resistance of RJB plus RBA is greater than RJC plus RCA? So if the thermal resistance towards the board side is much higher than the thermal resistance towards the casing side, what would be the final result? Circuit would melt, of course, circuit would melt, that's a physical result. Circuit would melt, and the device would be, there will be a reliability issue and it will fail. But in terms of analytically, if you look at this equation here, so what we can do is we can simply write it as RJB plus RBA, it comes out of the bracket, and then RJC plus RCA, and this is, now this term is much greater than this term. So if this term adds into this term, it still remains this term. So we can write the denominator as RJB plus RBA, it cancels out, and RJA would be equal to RJC plus RCA, right? So then in that case, if one resistance is very high, so that heat transfer doesn't occur from that side, then the total resistance between junction to air would be just the resistance which is least, right? So in that case, we have to design the system in such a way that we can ignore the resistance which is very higher in the magnitude as compared to the other one, right? So now I think let's go to one problem. This problem, I think you can all take out your cell phone so that you can do some simple calculations here, very simple calculations. So in this, what we have is, we have an electronic package with a junction to case to air, junction to board, and board to air thermal resistance given to us. They are 2.5, 15, 8 and 25. At the same time, I also want to have a little bit idea of what these magnitudes are, because further we'll discuss about a liquid cooling, and there you will see that this will change. Whether it will be higher, low, that we'll see, but just have a look at or have an idea about what these magnitudes are for the thermal resistances. So for junction to case, we have given 2.5 degrees Celsius per watt. For case to air, it is 15. From junction to board, it is 8, and from board to air, it's again very high, 25 degrees Celsius per watt. Now it is asked that what is the junction to air thermal resistance? Very straightforward. We can simply do 1 by R JA is equal to 1 over RJC plus RCA plus 1 over RJB plus RBA, right? So that is, the first part is quite simple. So I think you will be able to do it very quite easily. So we can simply write RJA is equal to RJB plus RBA times RJC plus RCA divided by the sum of all these four. So 2.15, 48, 50.2 degrees Celsius per watt, and this comes out to be 11.4 degrees C per watt, right? So the total resistance to the heat flow is 11.4 degrees Celsius per watt. Now second question is what we engineers mostly get. If this package dissipates 5 watt and the air temperature is 25 degrees centigrade, what are its case and junction temperatures? This is what is important for us, because here we are given that this device, it operates at, let's suppose 25 degrees centigrade. That is the ambient temperature. So if this package is dissipating this much of heat, then what would be junction temperature? Because junctions are more susceptible to failures. It is junction that have the maximum temperature. So well, in terms of heat transfer, it's very easy question, right? So just try, maybe it will be revision for you also to try heat transfer. So by definition, we know that RJA is equal to Tj minus Ta by Q. We can use this relation very simply, and then we can simply find Rtj is equal to Q dot Rja plus T ambient, and this would be equal to your 5 into 1155 plus somewhere around 82, yeah, 82 degrees centigrade, right? So you can also see that if the junction temperature would have been 40 degrees centigrade, this would have a further increment of 15 degrees centigrade. So it would have been close to 97 degrees centigrade. Now we know the junction temperature and we know the junction resistance. The third thing they have asked is to find its case temperature, right? And we just know the resistances towards case side. So how would we find that? Amazon का फ़ोन है, OTP भेजेंगे शायद ये, मैं गलत हूँ। So we are now being asked to find the case temperature. To find the case temperature, what we know is the thermal resistance between junction and case, and we know the junction temperature. It's again simple. So we can simply write it as R between junction and case is equal to temperature of junction minus temperature of okay. So but before that, we also need to find how much is the heat transfer that occurs to the case. We still don't know that. We would have this use this equation very simply if we would have known that what is the value of this Jc. We don't know that. So how will we approach this problem? So there has to be, it's very simple, there has to be some known here. What is the known quantity which I am writing as unknown? This is known, right? This is unknown. This is unknown. So it's not a good approach to write Jc. We could have done it for Ja because we know the ambient temperature. And whatever heat is being flown or being conducted into this casing, that much heat is convected and radiated towards the ambient. So we could have written it in such a way that RJA is equal to Tj minus Ta whole divided by Qjc, right? So now in this problem we have this is known, this is known, this is known, this is unknown. Now we get that. Qjc because you know we have this device, and when we define this resistance between junction to air, so we have two modes or two devices where the heat can transport from junction. It's either to the board or to the casing. So we want to know how much of the heat out of 5 watt it goes to board and how much goes to the casing, right? So that's why we are using Qjc. If we are defining it for the thermal characterization parameter, there we just need to take Q. So in that case it would have been much simpler, but here we are dividing your junction to air thermal resistance. No, we are not ignoring that. So what we'll do is this is between just junction and casing. If we write RJB, that would be equal to Tj minus Tb upon Qjb, right? So from this we will try to find this and then see how much of the heat has gone to the casing, and the remaining would have gone to the board, right? So here what we can do is we can write RJC is equal to RJA times Tj minus Ta. Tj we know it is around 82 degrees centigrade, Ta is 25 degrees centigrade, and RJA is junction to air is 11.4. Yeah, here. So from here we can find, yes, RJ डिवाइड होना चाहिए कहाँ पे? हाँ, QJC निकालना है. So then in that case we can simply write QJC is equal to RJ times this term. Oh sorry, divide. अच्छा हाँ. Sorry, it should be divide. My mistake. So here it is RJA. ठीक है? So now we can find the value of QJC. I think it would comes out to around 3 point something. 5 आया? फाइव आया है. Okay. 5 should not come. So let me also draw the circuit again, and then there is some mistake which we have done here. Which equation? अच्छा QC किया इसमें TJ minus TB TA. हाँ उसमें प्लस होगा फिर. हाँ अच्छा हाँ उसमें हम रेजिस्टेंस प्लस थोड़ी किया एयर वाला. So we have not added there your this one resistance, I think. One board. ठीक है, so we'll just do it again. So right now we are just at 82.5 degrees centigrade, and what we have to find is we have to find what is the case temperature, right? So please try to write the equation. Hmm? 8 point. कितना आया? टू 2.5 and 8. अच्छा हाँ, बिल्कुल. सो अगर वो एक 2.5 एक 8 है, so it would be 5 by x is equal to your 8 by 2.5. So in that case the Q would come out to be around 2.5 and 18, 1.7 and 3.1, either 1.5 or 3.5, around that, around the ratio of 1:3 का आएगा, है ना? So I think then in that case your Q from your junction to your casing, case it would come out to be your 8 by 2.5 times what is the value of that? 5. Sorry, 5 into 2.5, 5 into, sorry, 5.5 by 8. That should be it. Try to see what is the value. Three point. But this is also not right. Huh? So let us draw the circuit diagram in that case first. So we have this is your 82, this is your 25, and this one is your junction to case. So this is C, this is board, this is air, this is J. So junction to case is your 2.5, case to air is 15, and the next case is 73. हाँ 73 आना चाहिए, but एक बार दिखाते हैं कैसे आता है. Junction to board is around 8, and then we have 25. So we can just add these two individual terms. So it would be 17.5 and this would be 33, right? So it would be in that ratio. So out of the 5 watt, this is the path of least resistance, this is the path of more resistance. So more heat would travel from this side, less would travel from this side, and the ratio would be 17.5:33, right? So if we do that, we can simply yeah, so out of 5, let's say A plus B is equal to 5 watt. So around 1 point, close to 1.67. So close to 1.67 watt should travel from this side, and then close to 3.3 watt should travel from this side. Is it what is coming? ठीक है. So it's always better to draw the thermal resistance diagram. Next, we know how much heat is being transported from this side, and we also know the thermal resistances. So now I think it's easy to find the temperature. And the temperature would come out to be कितना आया? 73. Yeah, 73 is right answer. बिल्कुल सेम है. तो तुमने दोनों को इक्वेट कर लिया फिर, वो भी ठीक तरीका है. They can be multiple ways. So your final answer should be 73.8 degrees centigrade. So this is the temperature of casing. So it means this is quite a good casing. So that from junction temperature of 82 degrees centigrade, it's able to go until 73.8 degrees centigrade to the casing, right? Can you also find how much is the bore temperature? Amit, how much would be the bore temperature? कितना रहे? So the bore temperature comes out to be around 69 degrees Celsius. And this heat transfer is only occurring from the internal embedded heat pathways that has been designed in the system itself. ठीक है? We'll do a similar problem. अच्छा ये तो हमने एक पेज में कर लिया. ठीक है. So in this case we have a 40 mm by 40 mm by 2 mm package that is exposed to laminar forced convection airflow on its case. So in this we also have forced airflow on the casing, and the size of the package is 40 by 40 by 2 mm. The junction to all the thermal resistance are given. The junction to case is given, junction to board is given, and board to air is given. But your case to air is not given here. Of this package is 4, 10 and 25 degrees Celsius per watt respectively, and this dissipates 10 watt of heat. So what is the minimum air velocity to keep the junction temperature of this package below 105 degrees centigrade? So here we are designing a fan that must throw the air over this package so that the temperature at the junction, it doesn't go beyond 105 degrees centigrade. We are also given the temperature of the air, which is 25 degrees centigrade. So in this we are asked to neglect the radiative heat transfer. So we are said that let me draw this problem here. So we have your junction, let's say this is junction, this temperature is given that it should be less than 105 degrees Celsius. The T ambient is 25 degrees Celsius, and then we are given the thermal resistances. So if I draw the circuit diagram for this, it would be something of this sort, where this is maximum case, this is 105 degrees centigrade, this is 25 degrees centigrade, and let's suppose this is your casing, this is your board. So from junction to case it is 4 degrees C per watt, from junction to board it is 10, and from board to air it is 25 degrees centigrade. So the better approach would be first to find what is this value, right? You also given that the total heat transfer rate is 10 watt. This much of power is dissipated as heat, and then this has to flow through this circuit. So what we can do is, first we can find the resistance from junction to air, because we know the junction temperature, we know the air temperature, and we also know the net heat transfer rate. So what we can do is, first we can write R JA is equal to Tj minus Ta by Q. I think for most this should come out to be, is it right, 8? 8 is fine? ठीक है ना, ये overall 8 ठीक है ना? And once we know 8, we can write that 1 by RJA it is equal to 1 by RJC plus RCA plus 1 over RJB plus 1 over RBA. This CA is not known to us. Let's suppose this is X. X is equal to 6.3 or this, okay. So yeah, it's 6.37. So your RCA it comes out to be 6.37 degrees C per watt. Are you all able to solve it? No? So right now the industry requirement is to have a resistance of 0.02, 0.01, 0.015 degrees C per watt. And since, because the source from where I've taken this problem, it's quite an old source, so they were still dealing with at least 2 order higher junction resistances. You're not doing it? तुम्हारा काम तो यही है. But until this, it is quite simple. What is the next approach? what is the next after this? So once you find RCA, QC we need to find. Before that we need to find the heat transfer coefficient, है ना? And once we are able to find the heat transfer coefficient, then we can use the empirical relations to relate H with U, and then we'll find the U. Okay, so I'll simply do it. So what we can do is we can write RCA is equal to 1 over H into area of your casing, right? Here we have ignored the any radiative heat transfer, so we are just doing it for the your simple diffusion plus advection, which is the convection heat transfer. And using this we can find that your H comes out to be 1 over RCA times AC. Your dimensions of this board are given, so it would be 40 by 40. So 40 by 40 into 10 raised to power minus 6 meter square is your surface area, and RA comes out to be 6.37. So this H, it finally comes out to be well, what I've written is 98.12 watt per meter square Kelvin or degree Celsius, right? So at least this much of heat transfer coefficient is required so as to maintain the junction at 105 degree centigrade. And then further we can use the empirical relation H is equal to 3.9 times U infinity by L 1 by 2, and this comes out to be 25.3 meter per second. This should be the velocity of the air. Do you see something off here? As an engineer, very high velocity. This will throw away your package, right? Even if it's embedded on the board, it will be damaged. So it means that even sometimes the forced air convection is not enough, and we need to go for the liquid cooling. The advantage which liquid cooling gives us is that it has got higher K value, higher specific heat. So it is possible to make the system much compact when we go for liquid cooling. Or one more thing we can do, if we still want to stay with air, what else we can do? If we simply increase this area, if we simply increase this area, it means that if we use fins, in that case we'll be able to solve the problem with much lower velocity. Let's suppose that this area becomes, let's suppose that the area of the casing is amplified by 5 or 10. So it will reduce the value of H by 5 or 10 at the same time. It will be maybe 20 or 10 watt per meter square. And then if we use it here, this would come out to be at least 3 times less than this, or at least 6 times less than that, right? That is still of course that is also a little bit higher velocity, still doable with a fan or with any auxiliary device. Okay? So next we'll briefly discuss about this heat sinks. So heat sinks we use, or you might have studied this in your heat transfer also, that we discuss about fins, right? So heat sink is a collection of multiple fins that we use. Just a little bit revision of what these terms are. So what is fin effectiveness? How effective your fin is. And how do we calculate that? We remove the fin, we see how much is the heat transfer, and then we put the fin, we see how much is the heat transfer. We compare those, we get the fin effectiveness, right? Other important parameter, fin efficiency. What is fin efficiency? And these are sometimes confusing terms, but what is fin efficiency? In this we consider that, or we assume that the maximum heat transfer rate occurs from fin, and that will occur when whole of the fin is having finite thermal, the value of K. And the finite value of K would occur when same temperature would be there. So these are some simple terms which we have, of course we have used them when we study about fins, but yeah, sometimes we don't remember. Okay? So I'll just write these formulas here, and then we'll shift on to the heat sinks. So when we talk about thermal fin thermal resistance, it is equal to Tb minus T infinity over heat transfer from the fin, where Tb is the temperature of the base, T infinity is the ambient temperature. Let me also draw the fin here. Okay, this is your Tb, this is your T infinity, and the heat transfer which takes place from the fin is Qf. The fin effectiveness, it's usually given by epsilon, and it is the ratio of your heat transferred from the fin to the heat transfer when there is no fin, right? So it is given as Q fin over H times area of the base times T infinity minus, Tb minus T infinity, right? Usually it's prescribed that if the fin effectiveness is greater than 2, only then use the fin. Otherwise, the use of fin is like it's not suggested because of the various economic and other design parameters. Fin efficiency is defined as heat transfer which occurs from the fin to heat transfer which occurs on the fin in the maximum heat transfer that is possible. So it is also defined as Q fin by H. This here is area of the complete fin times, we assume that the maximum heat transfer would occur when all of the fin is at same high temperature. It is equal to the base temperature, which is Tb minus T infinity. So from these two relations, you can also find the relation between effectiveness and efficiency, and that would be epsilon is equal to all the terms would cancel. The only term that would remain is your AF by AB. So AF by AB times eta, right? Now let us talk about the heat sinks. So this is one image of the pin fin heat sinks which I have used here. So I'll draw multiple fins and we'll just call it heat sink for this case. So let's suppose this is your plate. On top of this we have one fin here. We have one fin also on the bottom side, and then we have one fin which is here, right? And we call this heat sink. Of course, the heat sink will have multiple fins, but for simplicity we are calling this a heat sink. And let me also draw some other parameters here. So the height of this heat sink we have kept is capital H, its width is W, the thickness of each fin is given as T, the gap between or the space between the fins is S, T ambient is the T infinity is the ambient temperature, and Tb is the temperature of the base, right? So if I have to write the net thermal resistance of this heat sink, what would it be? So the heat transfer is it in series or parallel here? Parallel, right? It's parallel. So we can write 1 by R heat sink, and here for beginning we are considering both convection and radiation. So we are writing Cr here, that is equal to what is the thermal resistance of one fin, that is Rf, into the total number of fins, because we'll add this and it will be number of fins. Let's suppose it is Nf plus what term? Plus the resistance which is where there is no fins. because that is also responsible for heat transfer. So that we can write as 1 by R unfinned. ठीक है? This is N. And here R finned, it can be written as 1 by efficiency of a fin times H times area of a fin, and the R unfinned, it can be written as 1 over H from unfinned, then area of unfinned. And unfinned area can also be simplified further. It can be written as area of the heat sink minus number of fins into area of each fin. That is the area of unfinned region. Now let us suppose that we consider one situation where H unfinned is equal to H. It means that the heat transfer coefficient from both the fins and unfinned area is same. That will further simplify this equation. So we can write it as R heat sink in terms of convection and radiation is equal to one over your number of fins into efficiency of each fin into H into AF plus the area of the unfinned region, which is given as area of heat sink minus number of fins into area of fin multiplied by H, which is same for both the cases, right? Further, if I have to write the area of heat transfer, the area from which the heat transfer takes place, that would be equal to simple number of fins into area of each fin plus area of unfinned surface. So NF into AF plus area of unfinned, and further I can write it as NFAF plus area of heat sink, which is this one, minus NFAF, or I can write it as area of AT minus Achha, this is one thing I have done a mistake here. So in the case of unfinned area, so this is already total heat transfer surface area. So the fins are totally considered here as well. So here it will just be the area of base. You know, it will not be the complete area. That's we already considered there. So AT minus your NF AT minus NFAF is equal to area of the heat sink minus number of fins times the area of the base. So this would be just base here then, not the whole thing but the heat sink of the base. And ultimately after simplifying all this, what we get is R of the heat transfer heat sink from the convection radiation is equal to 1 over the area from which the heat transfer takes place times the convective heat transfer coefficient minus times 1 minus NF AF 1 minus eta F whole divided by AT. That is the net thermal resistance of the heat sink because of convection and radiation. Similarly, we can find a, so you have one more class from 4. So similarly, we can find, I think you can do this as a homework. So try to find what is the effectiveness, or try to derive, I'll just write expression, what is the effectiveness, and then what is the efficiency of your heat sink. So the effectiveness would be equal to 1 minus NF by AT times 1 minus eta F times AT by area of heat sink of the base, and efficiency it would be eta T is equal to 1 minus NF over AT times 1 minus efficiency F, effectiveness F. So these you must derive when you go as a homework. Now let us solve a problem of this. Just one problem we have left with. So let us try to solve this problem. So in this, what we are given is that we are given an aluminium heat sink with a base dimensions of 80 mm by 80 mm by 5 mm. So it's 80 by 80 by thickness is 5 mm, and we have 20 aluminium fins that are 2 mm thick and 40 mm long. If the thermal conductivity of aluminium is 210 watt per meter Kelvin and the heat transfer coefficient is 15 watt per meter square Kelvin, find out the thermal resistance because of the convection and radiation and the base conduction thermal resistance of this heat sink. So we have to find first the value of R, the thermal resistance because of the convection and radiation, and then the base conduction thermal resistance. So what is the thermal resistance of the base of this heat sink that we have to find out. Okay? So the problem in such a way that we have a heat sink having dimensions, let's say this is 5, this is 80, this is again 80, and on top of this we have the fins, and these fins are total 20 in number, and its dimensions are 40 by 80 by thickness is 2 mm. Okay? So since these boundary conditions are not given, we can simply do the tip correction of the fins, which means that if we write the length which is corrected, that is equal to L plus A by P, that we can do, right? So L is already 40 plus area would be equal to your 80 by 2, so it would be 160 divided by perimeter, that would be equal to 80 plus 80, 160 plus 20 plus 20, 40 is 200. So it comes out to be close to, or 0.041 meter. Okay? Now when we do the edge end correction, we assume that then this is adiabatic tip, right? So then in that case we can simply find M. M is your square root of HP by KAC, and then we can find M into LC, and if we take the tan hyperbolic of this M into LC, we'll find the efficiency of the fin. So this relation is given as FNF is equal to tan hyperbolic of MLC. Okay? So once you find this efficiency, then you can use the relations here just simply to find out the thermal resistance and base conduction resistance. This is just a homework problem, so just do it as a homework. Okay? I hope you have taken the picture of this problem. So please try to do this in your homeworks, because we are still left with the liquid cooling and so ultimately what you will find is that the thermal resistance of the heat sinks because of the conduction and radiation, it would come out to be 0.505 degree C per watt. So in the last case we were not using the heat sinks, it was around 4, 2.5, 15, 8. Now it's 0.505 because we are using the heat sink. And for the base conduction thermal resistance of the sink, it would come out to be 0.004 degree C per watt. So now we have got an improvement in thermal resistance, or we have got a lower thermal resistance values as comparison to the when we are not using the heat sinks. Okay. So now just let us discuss the liquid cooling. So as we discussed that in the liquids they have high thermal conductivity and they have high specific heat. So it means that our system can be made much more compact, because for a given volume we can extract more heat out of the system, right? So that is one advantage. So I also wanted to do this calculation at home, but for a Reynolds number of 2000, it means we are still dealing in a laminar flow regime. If the in this case the diameter of the tube is around 10 millimeter. So for this diameter having tube 10 millimeter and the Reynolds number for 2000, we need the air velocity to be around 3.87 meter per second, and we need the liquid or water velocity. If we are using water as a coolant, it should be 0.09 meter per second. And when we go on to find out the heat transfer coefficient using these velocities, it has been found that the heat transfer coefficient of air is around 20 times less than that of the water. So even with the very low velocities of water, we are able to get around 20% more heat transfer coefficient in case of if we use water as a coolant as compared to air. So that means that we can make our system more compact by using the tubes which are much smaller than that also, because even for a lower Reynolds number we are able to get almost equivalent value of the heat transfer coefficients. So that is the main advantage of using liquids. Of course, liquid has also got certain challenges, that if the leakage occurs, then that's a problem. Liquids can be more corrosive. It can degrade the tubing of the system. When it comes to types of liquid cooling, we have direct and indirect cooling. In the direct cooling, we go for immersive cooling. So basically, direct cooling means that the liquid is in direct contact with the heated surface. So that is a direct cooling. As you can see that we have both the one phase and the two phase liquid cooling. In the two phase immersive liquid cooling, the boiling or the phase change can also take place, right? But this will make a system more compact, because here also the phase change is occurring, which can lead to bubble induced damages on the surface. This is just one of the graph which I took from ID Tech's research. This agency, it does research on the different cooling method which are used for data centers and the supercomputers, and they have just compared the application of single phase and two phase in terms of limited and good. So as you can see that in all the boxes, the two phase is not good as compared to single phase. If we talk about fluid losses, in two phase there are more fluid losses. It is also not a low cost, it has got high cost, because the number we need extra phase change to occur within the device. It has got high maintenance, but the cooling capacity of this is good. So that is the only advantage. So now the industries, they face with the problem whether they want to make their system more compact so that they can go for liquid cooling, or they want to go for reliability and low cost so that they can just go for a single phase liquid cooling. So right now most of the companies, they go for single phase liquid cooling, but recently with the battery cooling and other things, the need for two phases come up. Not battery cooling, the this IGBT cooling. It is usually used in electric vehicles, and this got very high flux. But still, most of the vehicles which we see around us, they all go for single phase liquid cooling, right? And the other one is the indirect cooling. In the case of indirect cooling, you don't have a direct contact of liquid with the heated surface. One very prominent example is the heat sinks or the cold plates. I have brought some cold plates here, so you can have a look at these cold plates. These cold plates are used by the industry, and these cold plates, they are basically used in your vehicles. So your vehicles, they have now they are coming with ADAS. ADAS is itself a computer. They have IGBTs. They have various other electronic devices which require very high level of cooling. In fact, the system on the front console in the car, that also requires this kind of systems to cool it. So all these heat sinks, of course, they are closed right now, but they have embedded channels inside them. And they comes in various shapes and sizes. So these are the bit smaller ones. And depending on how much is the weight you can take on, so on one side it can be a different material, so that the weight of this system is reduced. You can just share it with your other friends. So this is not 3D printed. This is the metal ones, and they usually go for the milling. So inside the dimensions are the microchannels width is around 120, 150 micrometer. So not very compact ones. Metal का इसमें वो है. So it depends on where the application is. So if the weight is not a problem, then they can use metal ones on both sides. But if the weight is a problem, then they usually go for one side. So they don't tell me what they like send me for testing, but they don't share with me what is the material. So I don't know what is the material. So they just bond it on the top of this metal. Two-phase liquid cooling means that the phase change occurs, boiling starts, because latent heat is involved there. So at a constant temperature, it can take in a lot of heat. So let's suppose that you want to design a system for your phone, and it's being given by the manufacturer that your phone chip, it will get damaged if it reaches a temperature of around 80 degrees centigrade. So what you would want that is that you need a fluid whose boiling point is little bit less than that of the 80 degrees centigrade. So when it reaches around 78, the temperature will not increase, but it will take in a lot of heat from the system. We already use that in research, yes. In application, no. Those are heat pipes. Those are heat pipes. Heat pipes are two-phase system, but heat pipe, those are the passive systems. When you say passive system, it means you don't need any pump. So these need pumps. These are active systems. Those are passive. They are just evaporation and condensation takes place, you know. Based on this, right. So those are passive. These are active devices. Okay. Now, in the end, let me discuss I was like very impressed with this paper. So you all are from thermal engineering background, right? And you all must be aware that it is very difficult for us to publish papers in journals like this, right? It's almost like very difficult. The work has to have very high novelty, right? And this paper demonstrates that they used a very simple method to achieve such high thermal performance of the system, right? So this work was done by the group of Mettioli. He works at EPFL in Switzerland, and this group is basically a power electronics group. So they make their own dies, they make their own electronic devices, and their devices they sometimes fail. So they try to make their own heat sink system. Usually what happens is that, I think one is still missing. That's the device. Okay, bye. So what usually happens is that this is designed by some other industry which works in thermals, and electronics is designed by some other industry like any electronic industry, and then they integrate this to make a system. So this is a system, right? When this combines with a device, it becomes a system. So what they have done is they have tried to make it monolithically. It means that on a single device they have channels, and then they have the electronic device as well, right? So I'll just show you by here. So what they have done is that this is the device, these are the gates, and these produce heat, and on the lower side they have kept it open for the liquid. So it means that there is no interface. When there is no interface, there is no interfacial thermal resistance, right? So here also they have used the MMCs. MMC is the manifold microchannels. The manifold microchannel means that we have a manifold. Let me draw the top image of this. So we have a manifold. Let's say this is your inlet manifold, and then we have an outlet manifold. Let's suppose this is your outlet manifold. Again we have an inlet manifold, and then we have an outlet manifold. So fluid enters the system from these inlet manifolds, and they exit the system from these outlet manifolds. But below these manifolds we have buried microchannels. So below these systems we have channels here. So if we see the front side of this channels, the flow is like this. So we have a manifold here, the liquid enters from this side, it goes under, we have the buried channels, it passes through it, then it comes out, and then it comes out from the outlet manifold. That is the flow configuration in these manifold microchannels. They have used this configuration, and they have really reduced the size using some techniques for microfabrication. And this image here shows the method which they have used for the fabrication, and this is the channel from which the liquid is flowing under the device, and this channels are fed by this manifolds. So we have manifold, it comes to the device under, and then it travels to the other manifold. And from here, this is one more image which they have shown in this picture. So they are comparing the SPMCs. SPMC is a straight parallel microchannel, and MMC is the monolithic manifold microchannel. So monolithic means just one solid substrate. On this they have designed both the channels, the fluidic system as well as the electronic system, and they have compared it for different channel widths here. So we have channel width starting from 100 micrometer all the way to 25 micrometer for the SPMCs, and for MMCs this is the manifolds. So this is the inlet, this is the outlet, and below this I think you can see it here that we have buried channels here, right? If you look very closely here, or maybe here, you can see some channels going toward that direction as well, right? I think I can use the now you can see, right? So these are the buried channels, and from these buried channels, these are the buried channels, these are the buried channels, and the device size is also shown by keeping it on a coin of a 1 euro cent. So this is such a small device they are using, and this is the flow configuration. So they have a GAN device on the bottom, the power electronic device, and then they have these manifolds and the buried channels below that. And using these channels, let's have a look at the results which they got. How to come out of this? Acha. Yeah, so this is their total experimental setup. This is the device where they are concerned, and there they have installed this device, and this is their fluidic system. So this is the IR camera they are using, this is the cooling device, and the inlet, flow meters, heat exchangers, and then the flow comes out and it's controlled by a PC, and then they are also using an IR camera for the system. This is the experimental setup they are used, and this is the beauty of their work. So this is their work. They have got a COP of nearly 10 raised to power 4. COP is defined as the desired output, desired effect upon the input. Input is just the pumping power which they are giving, and output is the heating, like the thermals which they are getting, and they are able to get the manage the heat of around 1700 watt per centimeter square heat flux. This much they are able to manage through just this system. So the gold standard is 1000 watt per centimeter square. Anything better than this is way good, and from this system they were able to design it for 1.7 kilowatt per centimeter square. And they have also compared their results with the other configurations. So they have compared it with the MMCs, which is the manifold microchannel. This is the monolithic one, the simple pin fins, the straight parallel microchannels, and you see what is the difference. So it is several orders of the coefficient of performance, right? So right now, especially in the power electronics where they use semiconductor or these GaN based devices, the aluminum nitride based devices, here because of the very high heat power flux, they are going towards the buried channels. And the fluidic system and the electronics, they are all developed over a same silicon substrate. So this is what the future has for this field, right? So I think कौन सा triangular है? So I think for the open ones, it is just simulations. For the closed triangles, this is experimental work. So that can be some, but this is simulation work. They have proven this using experiments. So what you can do is you can maybe have a look at this paper and then see that what these quarters have done, right? They did, yeah. So all the open ones, they are simulations, and all the closed ones, they are experiments, right? So I think with this was my last slide. So with this I end this lecture.